Hello, everybody. We've come to the very last of our problem-solving sessions. This is covering Chapter 30, and the problems will be due, or the homework problems will be due on Monday, as always. So let's get to it. This chapter concerns inductance, both self-inductance and mutual inductance. So let's look at the first problem in the recitation set. This is number 2 in the back of chapter 30. Determine the mutual inductance per unit length between two long solenoids, one inside the other, whose radii are R1 and R2, where R2 is less than R1, so R2 is the inner radius, and whose turns per unit length are small n1 and small n2. So you're taking the mutual inductance M divided by the length L of the solenoids. And the key here is you've got an inner solenoid and an outer solenoid. So the flux through the inner solenoid is just equal to the magnetic field inside it multiplied by its area, which is pi r2 squared. And then you want to figure out the flux through the outer solenoid, but it depends on which device has which solenoid has the current running through it, at least initially. But again, you can do mutual inductance problems two different ways, and whichever way you do them, you should get the same answer regardless. So that's an important check on your work, that you work one way, do you get the same answer when you work the other way? And you will if you've done this correctly. So let's move on to the second problem, which is number 8. An air-filled cylindrical inductor is 2,800 turns. So that's what capital N equals. And it is 2.5 centimeters in diameter and 21 centimeters long. So what is its inductance? So this is the self-inductance. How many turns would you need to generate the same inductance if the core were filled with iron of magnetic permeability 1,200 times that of free space? So mu is equal to 1,200 times mu naught. You put a piece of iron inside the solenoid, it magnifies the magnetic field inside the solenoid, which magnifies the inductance of the solenoid. And so you want to see how many turns you would need to get the same inductance with an iron core as opposed to an air core. And so remember, you're basically replacing mu naught with 1,200 times mu naught for the iron core. Then we move on to number 11. To demonstrate the large size of the Henry units, a physics professor wants to wind an air-filled solenoid with self-inductance of 1.0 Henry on the outside of a 12 centimeter diameter plastic hollow tube using copper wire with a 0.81 millimeter diameter. The solenoid is to be tightly wound with each turn touching its neighbor. The wire is a thin insulating layer on its surface, so the neighboring turns are not in electrical contact. How long will the plastic tube need to be, and how many kilometers of copper wire will be required, and what will be the resistance of the solenoid? So there are a few steps here. So you know the diameter of the wire, and so the length of the solenoid is equal to the total number of turns multiplied by that diameter. So you start with that and figure out, well, how many turns is that going to be? And try to figure out, well, how do you find N? And if you do that, you can answer the first part. And then how many kilometers of copper wire will be required? So each turn has the equivalent of one circle, or 2 pi r length of copper wire. And so you can figure out the length of wire from that. And then what will be the resistance of the solenoid? So that goes back to chapter 24, I believe it is. And, or is it 25? Excuse me, 25, when we talk about resistance and resistivity. And you have enough information here to figure all that out. That brings us to number 19 for the toroid of figure 3026. So again, you can look in your book. Determine the energy density in the magnetic field as a function of R. And so R1 is less than R is less than R2. So R1 is the inner radius and R2 is the outer radius. So you have a toroid. And integrate over this volume. So it's going to require some calculus and to obtain the total energy stored in the toroid, which carries a current I in each of its n loops. So what you're going to need to do, again, you figure out the energy density as a function of R. So we've figured out how to do the energy density. And it's going to be as a function of R because the magnetic field is a function of R. So you know what the equation is for energy density. You substitute the magnetic field inside a toroid, for B in that equation. And then you're going to integrate over the volume. So you're going to integrate from R1 to R2. And you've also got the height that you need to take into consideration as well. And so you're integrating, and then of course over the length of the solenoid as well. So you have the 3 dimensions. And so you're going to figure all that out. And it's actually not as hard as it may look initially. So you have your equation. It's going to be uniform for R, for a given R completely around the toroid. It's going to be uniform for a given R for any height on the of the toroid. So you're just integrating over R from R1 to R2. And that gives you the total energy that's stored. And you're going to solve for it symbolically. The current is I. You have capital N total loops. That brings us to number 23. How many time constants does it take for the potential difference across the resistor in an LR circuit? So this is the resistor, not the inductor, to drop to 3.0% of its original value. So the potential difference across the resistor for Ohm's law is directly proportional to the current, and the current, as we know, decreases exponentially. And so you're figuring out how many time constants does it take for the current to drop to 3.0% of its original value. And then the last problem is number 25. Determine the energy stored in the inductor as a function of time for the LR circuit of 30-6A. So remember, the energy is equal to 1/2 times L times I squared. And so L is constant, but I is obviously varying as a function of time. The squared term gives you basically one extra step in the derivation. So after how many time constants does the stored energy reach 99.9% of its maximum value? Again, the squared term gives one step into the extra step into the derivation, but you basically work your way backwards from the energy as a function of time to solve for t. And like I said, it's one extra step, but it's not a difficult step. And that brings us to the homework problems. A small thin coil with N2 loops, each of area A2, is placed inside a long solenoid near its center. The solenoid has N1 loops in its length L and has area A1. Determine the mutual inductance as a function of theta, the angle between the plane of the small coil and the axis of the solenoid. And keep in mind how you figure out the flux through the small coil. And again, this is another problem where you could figure out the mutual inductance 2 different ways, but you should get the same answer either way you do it. That brings us to number 9. A coil has a 3.25 ohm resistance and 440 millihenry inductance. If the current is 3.00 amps and is increasing at a rate of 3.60 amperes per second, what is the potential difference across the coil at this moment? And so you have enough information from that that you can figure out the potential difference across the coil. And that brings us to number 17. What is the energy density at the center of a circular loop of wire carrying a 23.0 amp current if the radius of the loop is 28.0 centimeters? So again, you have the energy density. It's you figure that out, or the equation requires knowing the magnetic field, but you know the magnetic field, or we've went over the magnetic field of a circular loop of wire, and so we're at the center of the loop of wire. So, you know, it's on the axis, but z equals 0. So that simplifies things quite a bit, and it's just like the lab experiment 10, where you have a coil of wire and you're looking at the magnetic field at the center. And so you know the current, it's 23.0 amps, and you know the radius of the loop, which will give you enough information to figure out the energy density. And then the last problem, and the very last problem, is number 24. It takes 2.56 milliseconds for the current in an LR circuit to increase from 0 to 0.75 its maximum value. So from 0 to 75% of its maximum value. Determine the time constant of the circuit, and then, and again, so you take the equation for current as a function of time, and you solve it for tau, the time constant, given the information that you have. And then B, the resistance of the circuit if you're given L. It's equal to 31.0 millihenries. So you're asked to figure out the resistance. So remember, tau is equal to L divided by R. You're given L, you solve for tau, you can then solve for R. Okay, so if you have any questions, do not hesitate to email me for help. And good luck. And we'll talk again on Monday. And have a good weekend. Okay, thank you very much.